Okay, in this video we're going to be looking at a volume of revolution, and I've chosen a pretty basic problem to do this with. And if you look up here, I've chosen these three equations to basically encompass an area that we're going to be revolving. So I've got half of this parabola. I didn't draw the other half over here because we're really only interested in the area between 0 and 2 in this example. So if you can picture this area bounded by this parabola, this vertical line, and this horizontal line, try to imagine what that shape would be if we took that area and spun it around the x-axis. We're just going to use the x-axis as our axis of revolution. So the area that I'm referring to is this area. Okay, so this area right here goes out to 2, and just try to picture what this would look like if you took this pink region and if you spun it around the x-axis. Doesn't matter which direction you spin it, but if you spun it around the x-axis, you can sort of picture that this is going to be not quite a cone, but it's going to kind of have it's kind of going to look like a cone. Okay, so I've decided to give you a little bit better visual with some software here. This is the exact same problem. This blue line represents x squared. You can see that this out here is the line x equals 2, and then y equals 0 is right here. And all I've done is I've spun this around the x-axis. Turns out we can kind of move this around and get a different perspective on what that looks like. And you can see that we have this little cone, okay, and gives us a good idea of what's happening. Now, the technique here is really to build disks and to let the integral collect all those disks. Okay, so what do the disks look like? Well, I can show you here. What would that look like if I give it a minute? There we go. So here I have 10 disks, and you can see that the disks here, I could even make less disks if I wanted to. I could say, well, what would it look like if there were only 5? And this sort of reminds us of a Riemann sum, kind of. Instead of building rectangles to approximate area, we're now building disks to approximate volume. So I want you to think about this. I want you to think about what each disk represents. Okay, the area of the base of one of these disks multiplied by this width is a volume. And then we're going to let the integral collect all those. Okay, much like the integral collects the infinite set of rectangles to approximate the area, we're letting the integral here collect the infinite number of disks in this interval. You can see that the more disks we have, if I do 15 disks, you can see that we start to get a pretty good approximation of what this volume looks like. Okay, there's 15 disks. Well, if we continue to let the I guess the widths of these disks, if we let them get smaller and smaller, let's see how small we can let it get here. Let's do 30. If we did 30, you're going to see that this is really going to start to take shape. Give it a minute here. There it is. Okay, so you can, I don't know if that's how well that's showing up in the video, but you can see that it's really starting to become the shape that we desire it to be. Okay, so that's one visual of what we're building and what we're doing. Now I've got another one to show you, and this is the exact same thing. And this one I'm not going to, if I let it be 2, that's kind of small, you might not be able to see it, so I'm actually just going to enlarge the area, but you'll get an idea of what it is we're actually doing here. If I took this blue area and rotated it about the x-axis, what would that look like? Well, usually the way I do this is I duplicate this area and you can kind of see this area sort of revolving around the x-axis, is kind of spinning. Okay, and I don't know, it's kind of plays a little trick on your mind, kind of an optical illusion there. I don't know if this is helping you or not. But now if I actually show what it built, here it is. You can kind of see this wire diagram of this cone that's being built. Okay, now let's show the disk, a random disk in there, and let's spin it a little bit, and you can sort of see this cone sort of take shape. Now that green disk in there is some random disk. Okay, and I can move the disk. I can move this disk back and forth, and you can see how this disk sort of builds the area, or at least builds the sides of this cone. Okay, so let's just get a couple of different perspectives here. Here it is from a different perspective, and we'll let the disk, we'll let the disk sort of grow and shrink. There's the largest it will be, and then the smallest is going to be back here at the tip. Okay, so if we let that area sweep, you can kind of see the area sweeping out this cone, and that's how our solid is being built. Okay, so let's go back to the picture here, and let's see if we can attempt to draw it. Well, the way I attempt to draw it is I reflect the function about my axis of rotation. The next thing I do is I imagine a couple of disks. And here's the outside disk. Here's the furthest one to the right. Okay, and then I build sort of a random disk, some random disk inside of here. What does that look like? Well, there it is. So this yellow thing right here, this yellow disk, is equivalent to this green disk in here, and that yellow disk on my drawing is kind of like this green disk here, and I just kind of build it in a random location. Okay, so that's this yellow disk. So what's the area of that disk? What's the area of it? Well, if I consider this radius right here, here's the radius of this disk, right? Whoops, why isn't that drawing? I know why it's not drawing. I need to be on that particular layer. Here we go. What's that radius right there? Well, how high is it? Okay, how high did I go? Well, the highest point of that line is right here. Where is that line? Okay, it's a y value. That y value is on this parabola. Okay, and it's x squared high. I don't know how far over I am. It looks like I'm in between 1 and 2, but I'm just at some random x location. So how high does it go? Well, it goes up to x squared. Okay, and this point down here is at 0. So what's x squared minus 0? Well, it's just x squared. So this radius right here is x squared. So we can say radius is equal to x squared. Okay, well, once we have the radius of this random disk, we can now think about its area. What is its area? Well, the area of a circle is pi r squared. So pi times the radius squared. Okay, and that radius in this case is x squared. Okay, so the final area then is going to be pi times x to the 4th. That's the area. This is the area of just some random disk that we could have just as easily have said, well, this has the same area depending on where x is. This radius right here is still x squared. Okay, so now what we're going to do is we're going to let the integral collect all of these disks, and I want you to think about where we're doing that from. We're collecting them from here at 0 all the way to 2, all the way to out here. Okay, and what's the area of one disk? Well, it's pi times x to the 4th. And now think about think about what this dx is. This dx is this infinitely small width of this disk, or height of I guess we're really building really tiny cylinders here. So we have an area multiplied by this infinitely small height of a cylinder. So what's area times height? Well, it's a volume. Okay, the rest is just some mechanics. We just integrate this now. And the way we integrate it, what's the antiderivative of pi x to the fourth? Well, it's going to be pi times x to the fifth divided by 5. And that's going to get evaluated. Oops, that's terrible. That's going to get evaluated from 0 to 2. And now we just use our fundamental theorem of calculus. Try to scroll up a little bit to give me a little bit more room. Okay, here we go. So now let's go ahead and evaluate this. This will be, I'm going to do it down here. I'm running out of room a little bit. Pi times 2 to the fifth over 5 minus pi times 0 to the fifth over 5. If you do this calculation, 2 to the fifth is 32 divided by 5 is 32 over 5 pi. And that's the volume. That would be the volume of this cone-like shape if we revolve this region about the x-axis. In the next video, we'll look at revolving this exact same type of function, except we'll revolve it about a different axis.